Hello, everybody. I'd like to continue in the broad sense this theme of alignment and talk, of course, in a very different domain. The problem of graph or network alignment that I'll get into, and the approach that we've proposed here to address this problem, which we call REGAL, which stands for Representation Learning Based Graph Alignment. So I'm Mark Heiman. This is done with two of my lab mates and my advisor, Denai Kutra, who some of you may have heard this morning, giving a highlight of several actually of the works that our lab has started to do that revolve in the space of techniques that I will be discussing in this talk. So thank you all, and let's get started. All right, great. So just for the motivation of what we're talking about, which is the problem that our entire research group focuses on, the problem of analyzing networks or graphs, right? And these occur in many places in a lot of data-related problems, and they occur at very large scales, right? So just to give you an idea, where you of course occur like in the web search domain, of course, where Google has like basically has a huge graph of web pages connected into each other, right? And then ranging from that, you have neuroscience, where the brain is itself a huge network. Email communications also are very large. Facebook is one of the, I tell the people when I just try to explain what I do to my work to someone who doesn't do this at all, right? It's a huge social network with billions of users at this point. And the lists of applications go on. At some point, many of you, in fact, may have encountered data that is graph structured, anything where you really want to learn from the connections between entities in your data, as opposed to just other metadata about the objects themselves. So now let me talk about the problem that we'd like to consider. The problem we'd like to consider says, what happens when you have more than one of these graphs? And in particular, what we want to do is we say you have two or maybe more. In this case, we'll just consider two for simplicity. You have two graphs, and you want to say, how do the nodes in these graphs line up? So if you consider the Facebook example, maybe you have another social network as well, like Twitter. You found one person on Facebook, where are they in the Twitter ecosystem or the LinkedIn ecosystem, right? So this idea of saying, let's find correspondences between nodes in networks is a very important problem. We want to do this in an efficient approach because our networks can be very large. Unsupervised means that we're not going to assume that you know some of the matchings and then learn even more of them. We're just going to try to learn this without any type of supervision at all. Of course, you can consider that, and that's a very realistic setting too. So we want to devise an unsupervised approach, and the main technical part that I'll talk about in just a little bit is this idea of node embeddings, which I'll use synonymously the term feature representation learning in networks. And that, of course, has a lot of connections to deep learning, which I'm sure almost all of you are familiar with. The essential idea is, instead of hand designing the exact right features you want to use for your problem, you give it to an algorithm, and give enough data, the algorithm essentially learns the features for you. Well, it turns out that this has come into play in the context of networks and network graph data mining, but not really for this task, and I'll talk about why that is when we get into some of the assumptions that we'll have to make on a technical level to actually get this to work. But because feature representation learning has so much potential to offer, as you can tell from the boom of deep learning, we thought that it would be really helpful to leverage it for this task, if possible. So before I talk about what node embeddings are, okay, well, so this is interesting. Oh yes, great. So, sorry. For a moment I froze, I thought that everything was showing up, but great. So why network alignment? Just to motivate this, right? So one of the most natural things that I alluded to even when introducing the problem, this idea of entity resolution across two networks, right? Linking user accounts in two different, for example, social networks. And that's a natural one, but it in fact occurs in many places in the sciences. We're starting to get into more technical things that perhaps practitioners in some of these fields would know even more about than I. But in a variety of biology, chemistry, other fields, you find this in business applications, like in marketing. You can consider this like a machine translation, right? Which of course gets into some other areas of machine learning and data mining, right? Trying to say, okay, these terms in different languages, you can also model languages based on using networks, right? These terms and languages are translations of each other, right? So in fact, the applications span vision, right? So basically all the fields that you can think of if you're an academic, right? We're doing research in computer vision or natural language processing, or all the fields that you might think of as like a practitioner of the sciences or in business, right? All of them, in fact, usually have some application of network alignment. So this problem is pretty well studied. But I will talk about some of the existing approaches and how they differ from ours, because the technique that I'm going to talk about now, this idea of node embeddings, is so hard to apply to this problem until this work. So what are node embeddings real quick? Essentially what we're doing, as I said, is I'm going to use this synonymously with feature representation learning. So we want to, for each node, we want to associate it with a feature vector. Now if you think of it, a graph actually provides a feature vector for each node. The feature vector for each node is its list of all its connections to every single other node in that network, right? Like, so what this means is if we're in the Facebook network, Facebook has 1 billion users, there's a feature vector associated with me, right? I'm on Facebook, right? There's a feature vector associated with me that just says, for all those billion plus other people, am I connected to them? Am I not connected to them? That's a very, very high dimensional vector, not something you want to work with. So these feature vectors, the goal is to make them much lower dimensional. And so that problem actually gets into what many of you might know as like dimensionality reduction. And dimensionality reduction often involves this idea of latent features. And I've tried to contrast this a little bit. I hope it's somewhat understandable. Latent features contrast with hand-engineered features, which are things that make sense. For example, in a network, it's a meaningful concept, right, to talk about how many connections someone has, right? Or on Twitter, right? How many people are following you versus how many people are you following, right? Those are very interpretable features, and it's possible to compute those and a bunch of other slightly more technical statistics about each node and put those together, and that represents the feature vector for a node. On the other hand, this idea of latent features, right, what comes up in, for dimensionality reduction, if you do something like PCA, that's also another method of learning latent features, and there the individual numbers might not actually be as interpretable in the feature vector. But the idea is that the geometry of these embeddings, that's what we call them, right, the latent features that you have, should satisfy some desirable properties. We're actually going to spend a lot of time talking about what those are in the context of network alignment. But essentially, nodes that are similar in some very rich and complex sense should hopefully have similar vector embeddings as well. And so that's essentially the goal of a node embedding, right? Is to say, we're going to go beyond these hand-engineered features that are, they might make sense to somebody, but on the other hand, it's not really clear what the best types of statistics to compute are, and they're also pretty rigid in terms of the notions, in terms of what they actually describe about an entity in the network. We want to go beyond that into these latent features, which although they might be a little bit less interpretable, actually are often more powerful. And this is something that, of course, right, the rise of deep learning is such because the features that these machines learn, although they are less interpretable, are often more powerful than what a human might think to design. So, right. Now let's go back. I want to talk a little bit about what previous works in network alignment have done, because like I said, a lot of them have not revolved around this feature-based approach or this feature representation learning-based approach. In fact, most of them eschew the feature altogether, and what they do is they try to solve an optimization problem. And what this optimization problem might do is focus on the adjacency matrices, right, that represent all the connections in the network. And they essentially try to solve a mathematical problem that says, how can we find a permutation that turns one adjacency matrix into the other. That's what that formulation that I proposed does. I am trying to summarize at this point a great deal of the literature in one equation, which is not really possible to do. So just know that there are many ways to relax this problem, add additional constraints or side information. But what I do want to summarize is some of the drawbacks that all these approaches have. At the risk of painting with a broad brush, what a lot of these approaches share is at least one or more of the following drawbacks, right? One is that they are computationally expensive, right? That solving this optimization problem, as you can imagine, is not cheap, and existing algorithms to do it often operate in perhaps cubic time in the number of graphs, which is perhaps fine if your input is like if you have 100 nodes. It's less fine if you have 1,000 or 10,000 or 100,000, millions, billions, right? In that case, slow algorithms just makes for a lot of pain. The other problem is that they can often find like one-to-one or hard mappings, which means that they say this node aligns to this other node. There's no choice about it. That's just all they can tell you. If we're right, we're right. If we're wrong, we're wrong. We'll see that we don't necessarily need to follow that constraint. Finally, this formulation, as I mentioned, there are so many papers because they all tweak it in some ways, but this is exactly the point, right? You need a very different formulation, an entire different direction of technical innovation if you want to handle even a slightly different setting, if you have side information in your graphs. Even if your graphs have different sizes, which is of course something you'd expect in many cases, these all require different formulations. So in contrast, our approach, as I said, is to learn these feature representations for the nodes. And then at that point, we just simply match nodes if they have similar feature representations. So it gets very easy as once we actually get the right feature representations. I'll just tell you that much in advance. Some of the challenges, though, are getting the right feature representations. We face two challenges here. The first is the comparability of embeddings across networks. Like I mentioned, we are defining this problem over 2 or more networks. In a sense, it's almost like 2 entirely different ecosystems, right? The Facebook network and the Twitter network. What goes on in one and what goes on in the other, it's not always easy to generalize across them. And I'll explain that more throughout this talk. And then another challenge is just the problem of scalability. Here's a framework. I'll talk about some of the tricks we do to try to speed it up. Not just so we can do even better, much better than Cubic, actually. All right, so let's get on to the proposed framework. So given 2 input graphs for simplicity, you could extend this to more graphs if you wanted to. The first step we're going to do is we want to get some sense of the node's identity. And this is a term that we'll definitely have to unpack more. I'm just going to give a high-level overview at this point. And once we do that, at that point, we want to turn these into node feature latent features that essentially preserve the similarity of the identities between the nodes that we extract. Once we do this, this step constitutes our node embedding step, which we call cross-network matrix factorization, xNetMF for short. Once we do that, actually, the alignment step will show 1 or 2 tricks to make that a little bit faster. But a lot of it is going to focus on how do we get this xNetMF method? Why is it? What assumptions are we making that make it suited for this task? And what I hope that you get away from this, even if network alignment isn't your thing, even if networks aren't your thing, is maybe this idea that we're working in this idea of feature representation learning, this like learning latent features. And sometimes people think that latent features are a black box, which in some ways is true, that they are in fact less interpretable than traditional features that were designed by humans. But that's not to say that they're just magic and you just take them as given. While it is true that the individual numbers, our point is not to hand tailor them exactly. That's the whole point of learning them instead of tailoring them. We can think at a high level about what assumptions we want to make for our problem. And then we can say, given these assumptions, how can we make our latent features respect some of the assumptions that we need to be respected for this problem? And so through the course of this talk, I hope that you get some idea of how we did that in the context of a graph or network. All right, so examples of node similarity, because it's going to be very important. We want similar features for similar nodes. What do we mean by a similar node is what I'm trying to explain here. So this idea of node proximity is the way a lot of node representation learning methods work. They essentially say if 2 nodes are close in the network, they should have similar features learned for them. For example, nodes 1 and 2 are close in the network. They're connected in this tiny example. Nodes 1 and 4 are not connected. So you would say 1 and 2 should be closer than 1 and 4. On the other hand, if you are taking a different perspective, which we're going to take, spoiler alert in this talk, this idea of structural identity, you want to say which nodes kind of behave like each other in the network. And in this case, what you'd say is 2 is actually connected to everything else, right? It's kind of the hub node, and everything else is on the fringe. So in that sense, nodes 1 and 4 should be more similar to each other, and 1 and 2 should be a little bit different because 2 is a hub node and 4 is on the fringe. So the reason this makes sense is because, or the reason this is important is because in the task of network alignment, nodes in 2 different networks are not in proximity, right? They exist literally in 2 different network universes, as it were. So this idea that 2 nodes that are in different networks should align, right, will have similar embeddings, that will not happen if we try to have our embeddings preserve this node proximity. It'll put all the nodes in one network close to each other, all the nodes in another network close to each other. Who knows what's going on in between? On the other hand, what we can say is, if the nodes have similar structural behavior, right? So maybe we can say, okay, these nodes are both hub nodes in the same, even though they're in 2 different networks, they're both kind of hub nodes. They're connected to a bunch of other nodes. That might mean that they are kind of the same entity, right? Kind of like, name your famous celebrity or rock star in your area of work, right? They're probably pretty popular, right, in both, Twitter and, I don't know, LinkedIn or something. So we're making that assumption, and I should note at this point, of course, that that assumption doesn't always hold, right? So there are some people who are very active in one network and not in another. Just to use a social network because I personally find it to be the most relevant example, to use that analogy, right? So we are making an assumption here, right? That essentially if two nodes have similar kind of structural roles in the graph, in two different graphs, that means that they might align. So anyway, so now that we've done this, we were saying we don't want to focus on proximity, we do want to focus on structural identity. It should be noted that other works have found this useful for learning across multiple networks, although not in our exact formulation. We also, if you have additional side information, right, like attributes about each node, those have been found to be useful for network alignment before. We'll allow for a way to incorporate that in a formulation as well. All right, sorry about that. I'll try to pick up a little bit faster, right? So these two are the quantities we want to focus on, not node proximity. Essentially, these quantities should be node ID invariant. This maybe is on a little more technical level to what goes on in a lot of these techniques that are used to learn the representations. Okay, so structural identity, what do we mean by that and how do we actually capture it in a network? So like I said, our goal is to have comparable embeddings across networks. And to do this, the first thing we want to do is we want to say, okay, what are the degrees of my, not just me, but of my neighbors? And I want to not just consider my immediate neighbors, but like my neighbors of neighbors, right? That provides even more information. I can go out to K, as it were, steps away from me. Of course, the people who are 6 degrees of separation, right? Everyone's 6 degrees of separation away from Kevin Bacon, or I think that's who it is, right? So so that's a little bit less informative, right? I mean, like I shouldn't have that much influence on the features we learned for Kevin Bacon, much as I might like to think otherwise. We do want to discount those, unfortunately, for me. So in this, I mean, this technique is, of course, similar in a lot of other diffusion processes that are defined over graphs. So anyway, so the point is, okay, analyze the behaviors of your neighborhood as defined by the degrees. That's what we're going to start with. So for node A in this little network, right, so we've kind of highlighted it's one hop, right, B, C, D are its immediate connections. E is in its two hop neighborhood, that means that there's a path of length 2, A to D to E that gets to E. Anyways, right, so we want basically coming up with the degree distributions of the k-hop neighborhoods. Just one little note here, when we actually record this in a vector, you could have just one vector of all the possible degree values and just say, okay, first entry is how many nodes have degree 1, second entry is how many nodes in the neighborhood have degree 2. You can also kind of combine it in this logarithmic binning approach, so you can say the first entry is how many have degree 1, then degree 2 through 4, then 5 through 8, right? So the larger the degree is, the more things get lumped in a bin. And that is because a lot of networks follow this, what's called a power law distribution, right? Only a few nodes have really high degrees, right? Only a few people have like 1 million followers on Instagram or whatever, right? Like, so those people kind of get, having like 1 million versus 1,000,001 is a lot different than having 100 versus 101 connections, which is a lot different in turn than having 1 versus 2, right? Smaller differences are important in lower scales. So that's just a little thing that we do there that does make things a little bit more robust and makes the vectors a little smaller. As I said, we're going to come up with one of those degree distributions for each of the hop distances, right? For my neighbors, neighbors and neighbors, et cetera, and then combine across different hops with discounting the further away ones, right? So this is just a little bit example that you can work through, right? So for example, in the one hop neighborhood, the node D has one connection, has 2 connections, excuse me. So that's why there's a 1 in the second bucket. There is no logarithm in here. It's too complicated to fit into a diagram. B and C only have 1 connection, so there are 2 nodes that have the 1 connection. If you're looking at the D1A, and then no nodes in this case have 3 or more connections. We could go through this example. This is just to see if you want to verify for yourself how it's a little math exercise, I guess, how you actually do this, right? But essentially what we get is we get this, for each node we kind of get the distribution of degrees in its neighborhood, generalized to several hop distances, so that you can get information at a variety of scales that kind of informs, it tells you something about the node itself based on something about what its neighbors are like. All right, so now that we have that sense of that, we want to say, okay, these allow you to define some sense of node similarity, right? Nodes that have similar neighbors and similar neighbors and neighbors and so on, right? You can imagine just comparing those vectors that we have, give you some type of node similarity. To get latent features, a lot of other approaches avoid what we call random walks. That's what the RW says. Those approaches tend to be computationally expensive to sample. So Just for the record, that's what we're avoiding. Instead, we're going to use this matrix factorization formulation. And what we're going to be looking at is a similarity matrix. Basically, what this is essentially is it is comparing the similarity of nodes based on their structural distance. The structural distance depends on the degree distributions and the hops like on the previous slide, and also your attribute distance, right? And so the similarity between nodes is basically a function of how similar they are based on those other things, right? And then you just turn a distance measure into a similarity function. So the reason is because a lot of state-of-the-art techniques for learning latent feature representation nodes, it's actually been shown by some really interesting work that essentially all they're doing is factorizing a similarity matrix. And here's a similarity matrix that we're using for this problem. Basically what they differ in is the exact similarity matrix they're factorizing. It's actually really interesting because a lot of these approaches that are using like neural network-based approaches that look like a very different architecture actually can be shown to be essentially be doing some type of matrix factorization. So essentially what we're like is we're just like, okay, you know, cut the crap, just do the matrix factorization. We're actually going to find out how to get out of that even. So we're still like, okay, fine, you know, matrix factorization can be done. It can be done for very large networks, right? See Netflix and others, right, with the movie challenge, right? Very, very large networks. But how can we avoid even doing that if we really want to? And so we're going to look at this idea of implicit matrix factorization. So essentially what we're going to note here is that we don't actually need to compute this entire matrix S. We don't have to compute all the elements in it, which basically, if we did, what we'd be doing is we'd say, compare all the nodes in one network, you know, to the other network. Or actually these networks, you can even embed them at the same time. So that's essentially saying, compare all the nodes in both networks to each other, right? How can we avoid doing all the pairwise comparisons? It turns out that we don't actually need all the comparisons between all the nodes ever to form meaningful feature representations for each node. So here we just basically introduce a little trick to get embeddings for each node, but actually only compute some of the comparisons. And so the intuition behind it is we are going to focus on computing only a few landmark nodes. And so we try to illustrate this with just picking out some nodes, which we illustrate by yellow strips, and compute all the similarities of these nodes to the landmark nodes. We also have a landmark to landmark similarity matrix, and this is leveraging some other techniques for low rank matrix approximation that have been used for other areas of machine learning. So really, I think what you should remember is essentially that the node embeddings are essentially expressed. Did I? No, sorry, I thought I lost my mic for a minute, but it clearly didn't. Okay. All the embeddings for the nodes, they are expressed in terms of similarities to only a few randomly chosen landmark nodes. And this allows us to get a low rank approximation of the full similarity matrix, but now really we only have to compute similarities to the landmark nodes. How many do you have? We denote this quantity p. We'll actually show that essentially we make it logarithmic in the number of nodes in the graph. It's also actually common to just pick a fixed number for the dimension of your embedding. A lot of people use 128 because powers of 2 are very popular for computer scientists to use. So that number is not important, but what you should know is it's certainly much, much smaller than the size of the graph, right? So that means that instead of computing n, if you just want to consider n nodes across all the networks, right? Instead of consuming n by n pairwise similarities, or you know, O of n squared at least, okay, then you are really be n choose 2. Then instead we are computing n by p, which is a lot smaller. So just as an overview of what we're essentially doing, right? So the typical approach on the right is essentially would compute the entire matrix S and then factorize it, which basically means it compares every single node in the graphs to every single other node, which is still meaning you're doing that if you have n is thousands, tens of thousands, okay, well that's not so bad actually. It's very easy to do quadratic, but like, you know, millions, getting a little dicey to compare all pairs of things. And then it would factorize that matrix using whatever your favorite matrix factorization algorithm is. Here essentially what we're doing is we're saying, we know the decomposition we want thanks to the Nystrom trick. Let's just only compute the entries we need to compute the decomposition itself. Instead of doing all the work and then just learning the decomposition anyways. Since we already know it ahead of time, we can just form it directly. Right, so anyways, it should just be noted this is slightly more arcane for academic purposes, but there's actually reasons we're doing this. It's similar to some other node embedding methods in a simplified sense. We can basically, essentially, we didn't just pull this out of thin air, just in case anyone was wondering. The last step we'll say, after we have these node embeddings, like I said, now this is the easy part, right? The hard part is actually getting embeddings that satisfy the assumptions we wanted to make for this problem, right? Specifically this idea of learning latent features for nodes that are comparable even between nodes in entirely different networks that have no connection to each other. Once we do that, things are a lot simpler. All we do is just say, okay, nodes that have similar embeddings, they should align. And to do that, we can use data structures like KD trees. So instead of just computing all the pairwise comparisons of node features, we use a KD tree, right? And that's a data structure that's used to find, for efficient similarity search. There are others as well. And this approach, it should be noted, we don't have to find just the top single most similar node and return that as your embedding. We can find the top 5 most similar nodes. And we can say, here's the probability, right? If we take the embedding similarities as some sort of probability. If you want, we can do that as well, right? So that's what we mean by soft versus hard alignments. We can propose more than one possible embedding and even a likelihood of it being the correct embedding if you wanted to. All right, so this is a simple greedy approach, right? Like I'm just saying each node is matched to its most similar embedding, right? It's compared to some of the other work that the methods in the literature do and the optimization problems they solve, this is actually almost embarrassingly simple. And perhaps in the future, I will talk about this later, there are extensions that can be made if we do consider more complex approaches. But actually, what's interesting is that it can work really well if the features themselves are comparable. All right, let's talk about some experiments, so that way I'm not talking forever. And so some of the baselines are basically they mostly revolve around optimization or other spectral approaches to the problem network alignment. And we propose our method that uses the proposed embedding method that I call cross-network matrix factorization, as well as some baselines. These should just mean are 2 approaches that are other node feature representation learning methods. And the second one satisfies the property, kind of like ours, of preserving structural similarity as opposed to proximity in a single network between nodes. Our setup, because there's often really not ground truth alignment information where we don't necessarily know, unless we're Facebook or something, how the people in Facebook and LinkedIn connect. Our setup is just going to be one where we're going to try to align a matrix essentially to a noisy permuted copy of itself. And this is something that a lot of people in the literature do because unfortunately a lot of us don't have access to data that contains ground truth matchings across networks. So we'll study how the noise impacts their methods. And we apply this to structure, and also if there's side information, we also apply it there. So just so you know, accuracy, our methods do tend to do better than other baseline approaches that don't use embeddings, or node defect, which tries to preserve node proximity data embeddings all the way to the bottom, doesn't do very well. There is some susceptibility. Our embedding method does tend to take a hit as the noise increases. And one thing I would say is that there is some baseline measure of alignments that a lot of nodes can find, right? Like it might not be too hard to find, I don't know, Justin Bieber, right, in Twitter or something. I'm just conjecturing. I haven't looked up Justin Bieber's Twitter following or anything. But I would imagine that compared to finding me in Twitter, it would be a lot easier to find Justin, right? So there's some approaches a lot of others can do. Our approach, because we have these really rich feature information, we can find other more nuanced approaches, right? I could find someone like me, perhaps. When there's little noise. When there is more noise, one of our ongoing approaches is how can we make this do a little bit better, right? So the approach does converge closer to the baselines. In fact, structivec actually, one thing to its credit, this other variant of our method where we plug in existing method structivec is a little bit more robust to the noise. The problem is that structivec, and I can talk about why that is, some of the assumptions it also makes it, very computationally expensive. And also structivec, it should be noted, does one other thing. It does this random walk-based sampling. Essentially, all you should know about it is the word random. It introduces some randomness into the process that automatically clouds some of the alignments that are being made, and which is one of the reasons that when there is little noise, it still can't fully take advantage of that, just because it's fundamentally limiting itself by the techniques it uses. All right, so I want to talk a little bit about how we use this if you have side information. We consider both some synthetic attributes, and in this network, we consider there's a real attribute. And that attribute it's a categorical one, it can have any of 29 values. We compare, there's only one baseline that I know of that performs alignment of networks that have side information for each node. And essentially, that method can actually do very well if you have very little noise in the attribute and you have very good information. So either a lot of attributes or one attribute that has a lot of information because there are several values it can take on, right, which gives it more discriminative power. Otherwise, our method does a lot better. And it should also be noted that the time comparison, right, we are much, much faster than this other approach, which is called final, because as it uses that attribute information, it takes more time. This does suggest that final is able to use attribute information very aggressively, right? It might take more time, but there could be extensions of our work to also try to be more aggressive in the way we use attribute information. Really, the way we use it is it's preserved in the node embeddings in one of the terms I mentioned earlier in the node similarity. All right, just so you know about scalability, we go up to consider synthetic graphs of up to 1 million nodes just to see what happens to the scalability of our approach. And essentially, it runs faster than quadratic time, which is really what we're looking for. Most embedding methods take at least quadratic time because essentially they're running up somewhere. They are running up into this all pairwise comparison. You compare all the nodes in one graph to all the nodes in the other graph. And we've introduced some tricks to not do that in the embeddings, right? When I said we don't make this big node-to-node similarity matrix and factorize it, right? We have our little nice strong trick. We don't do that. At the alignment step, we use a KD tree, right? We don't compare all pairs of nodes based on their embeddings, right? So these are two things that allow us, we verify, that allow us to get around this quadratic bottleneck that almost all, if not all, network alignment methods that I'm aware of come up against. All right, just to wrap things up, so we have a little bit of time for questions. Some of the conclusions you can take away are, so network alignment can benefit from the node embedding or feature representation learning. So if what you should get away from this, right, is that even if you don't really care about network alignment, it is yet another task that feature representation learning can be applied to with some benefit. But what we noted, right, most of the time was spent setting up the node embedding method and saying, what assumptions do we need to satisfy, right? In particular, in a network, we can't just say, okay, nodes are connected to the network. That means they should have similar feature representations. Well, that'll give you feature representations that are similar for the nodes within one network, but for nodes in another network, who knows, right? So we thought about that and we said, okay, let's come with a new node embedding method that says nodes that are structurally similar, right, which makes sense even in different networks, right? That, like, if I can be connected to a bunch of people who are connected to a bunch of people, right? That's a concept that is portable across networks, right? So we thought about that and we preserved that in our embedding methods. So the idea is we didn't just say, okay, node embedding, feature representation learning, latent features. We didn't just treat it as a black box. We said, what assumptions do we need to make about this problem? How can we be sure that those are satisfied in our feature representation? And then also, as I mentioned, we thought about some scalability requirements because of the nature of our problem and showed how in both the feature representation learning and the alignment step, scalable methods to get around the all pairwise comparison bottleneck can make your network alignment so much faster. All right, thank you very much. If you have any questions, I'd be happy to answer any. And yeah.